Thank you.
And Professor, is there any way you can move the clicker position? It's in front of a word that I can't see. Or is there anything above before collision?
There is just dots, okay? At this point, you are fine, okay? It's not hiding anything there. There, you see that? Okay. So it is, this dot means total final momentum after collision. Yes, so this would be total initial momentum before collision, right? So momentum is product of mass and velocity, m1, bi1, or b1i. It's just a notation, right? So this is momentum of object 1. And we have another object that has a momentum before collision, means we need to write m2, bi2, or b2i, okay? So that's the total momentum before collision. So that's the pi. And you can do the same thing for pf, okay? So that's how we use it. So now, going back to this slide here, let's use that idea to solve this problem, okay? So, in this case, there is collision going on. So that basically tells us that we can use conservation of momentum rather than kinematics or Newton's law of motion, okay? And so conservation of momentum tells us that total final momentum is equal to total initial momentum. So total final means there are two portions. So portions for us, for momentum, is just mass, okay? So we want to write m1, v1, something like that. So which one is m1, which one is m2? So we need to distinguish. So usually it's helpful when we do something like this. Let's say here it says Jack Matt, right? So let's say Jack is portion of interest number 1 and Matt is portion of interest number 2 or portion of interest 2. Okay. So now when we write M1, that means mass of Jack. So that's what we are writing. Okay. So let's write those down. So what are the things we know? So I can first write formula if I like, or I can just list the things I know in terms with the proper subs. Okay, I can do that. So for example, here I can say, okay, so there are two portions, two masses. So now I can write total final as momentum, final momentum of mass 1 means it's going to be final velocity of mass 1. So that's the final momentum of portion 1. And I need to write same thing here for portion number 2. Okay, so basically they are same. Only difference is now one portion means subscript 1, second portion subscript 2. That's it, right? So that's the total final momentum. Now I need to repeat this for the initial. And again, portions are same. So that means M1 and M2, they're going to be same. Only difference is now velocities, okay? And what's the difference? They're going to be velocity of portion 1, velocity of portion 2. And we denote that by subscript I, initial, okay? So that means I can just copy this. Oops. Huh, what happened? that wasn't the plan. I went behind, looks like, suddenly. So I can just copy this M1 B1, but this is initial, so B1I. And if you like, you can write, let's say B1I or BI1, okay? It's just a matter of preference, or just be consistent, you should be fine, right? So one more term here. So I copied this, I just replaced F by I. So I'm doing the same thing here, M2, BI2. So in this case, what are we looking for? What is the velocity of the jack after the collision? And jack is number 1, so that means BF1. See, jack is number 1, that means BF1 is what? So that's what we are looking for. So what other things we know then? Do we know everything else? I think so. The masses are there, right? And these velocities are there. But we have to be careful while writing the velocities. They are vectors. So we need to take account of positive and negative sign for the direction. Okay, so only that's the thing we have to be more careful once we write the formula and figure out, what we are trying to find. So masses, they being scalar, we don't need to worry about that. So mat means number 2, so M2 is 88 kilogram, and M1 is 44 kilogram. Hey, one is double of another one. If you like, when you see this kind of number, and if you do not want to play with these big numbers, what you can do is you can say, okay, M2 is 2M1, or M2 is 2 times M1. You don't have to, but you can. And sometimes this is going to simplify problem a lot. Okay, so that's that. And what other things we know? Let's go back here. Matt, so he bumps with Matt because his speed is 4.4 meters per second. So here Jack has the initial speed, and Jack is number 1. So that means velocity, and this is initial velocity of number 1. So BI1 is 4.4 meters per second. So is it positive or negative?
Negative.
Negative. So positive or negative?
Negative.
Negative. So how do we, write positive or negative? It can be positive or negative. That's kind of tricky. So we need to first assign which way is the positive, right? So if you are assuming it's positive, that means if you are saying it's positive, that means you are assuming that whatever direction they are initially moving is positive, right? It says, okay, bumps with Matt. See, they are moving in same direction, right? So let's say positive, okay? Assuming original direction or initial direction positive. Okay. Now we have another velocity. Matt is moving a bit slower, so that's why the bumping, right? So that means it's going to be BI2. And since they are moving in same direction, what happens? We can say that is positive 4.2 meter per second as well. And we could have said these negative, okay? We could have assumed that negative. The final result would be same. Okay. So we have one more speed. What is the velocity of Jack after the collision if Matt's new speed? So after collision, we are saying those are the finals, right? So that means it's going to be BF, and Matt's speed, it says 7.0 meters per second. So Matt is number 2. Oh, let's see, what is the velocity of Jack? So yes, Matt's speed is given. Matt is number 2, so that means it's BF2 is 7 meters per second. So now here, is it positive or negative?
Positive.
Positive. And how do we know that's positive?
Because he's still going in the same direction.
So yes, so see, this guy comes here. Let's see. So Jack is skating behind. So Jack is there and Matt is there, right? So he comes here and bumps. That means this person not gonna reverse the direction, right? So Matt gonna just keep moving in that direction. See, the speed increased, so must be in the same direction. So here it's not obvious. We need to a little bit think about it, right? So BF is that. So now what do we want? BF1 is what? So if we get positive, that means after bump, even after the bump, Jack continues going in the same direction. If we get this negative, that means Jack, after bumping, gets reversed. Okay, so let's say if there is a car and there is a truck, if truck bumps on the car from behind, what's gonna happen? Most likely, truck gonna just keep moving in the same direction without reversing the direction. But let's say there is a car coming and hits the big truck. When I say truck, I'm not talking about mini truck, I'm talking about big truck there, okay? So if car were to, come from the back and collide with the truck, most likely car gonna just bounce back rather than keep moving in the same direction, especially if car is moving really fast, okay? So it depends on situation. So we don't know for sure whether BF1 is positive or negative, and we don't need to. We can just find it out because we know everything else, okay? So now you can plug in everything here, but before plugging in, I always like to solve for the thing, okay? But you don't have to. But since I'm looking for BF1, so I'm keeping this term and moving this term to the other side, means just that gonna be negative. Everything else is just, I'm copying everything, see? And this is gonna be negative when it moves to this side. And by the way, oops, this is M1. And if you were to replace this M2 by 2M1, you don't need to plug in masses because all mass becomes M1 and they're gonna cancel. Or you can plug in 44 and 88, doesn't matter, okay? So now, what is BF1 then? Everything divided by M1, isn't it? So when we say everything divided by M1, that also means every term divided by M1. So either way is same, okay? So for example, 4 plus 4, everything divided by 4, what is that? 8 over 4 is 2, right? Or this could be 4 divided by 4 plus 4 divided by 4, which is also 2. It's the same thing. So yes, I can just draw a big line and write M1 underneath, or I can do this, M1 BI1 over M1. Each term, divide each term, it's the same thing, okay? So by doing this, what's the advantage? I can cancel M1, so I don't need to worry about those masses plugging in and punching in the calculator. But of course, you are free to do whatever you feel comfortable, okay? So M2, let's use M2 as a 2M1 and see what happens. There is M1 coming from that side, and that cancels the M1. So that's what I mean when I said, okay, you don't need to use those number 44 and 88 if you were to use this idea here. So that cancels. So that means what I have is VI1 plus 2VI2 and minus 2VF2. That's it. All I need to do is plug in those numbers, and based on what I have written, you should get negative 1.2 as the answer. Are you getting that?
Yes.
Yes, that's what I got.
Okay, great. Okay, that means you are doing it right. Okay, so that's what it means. Okay, so that's how we use conservation of momentum when two objects are, colliding like that. So we need to take account of the sign of the velocities and plug them correctly while solving them. Okay. So here is a bit summary about collision and conservation of momentum. Let's see, what do you remember? Oops. Okay, 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, so let's see what we got here. B and E mostly. So if you are choosing E, that means you are choosing B as well. And if you are choosing D, you are choosing all of them. as a correct. Okay. So let's talk a little bit about it. So if I'm choosing just B, that means, yes, so that's total momentum after collision is total momentum before collision. So that's a conservation of momentum. So B seems correct. How about A? Larger mass, momentum of larger mass is larger than momentum of smaller mass. Is that always correct? Always true? Momentum is mass times velocity. Larger mass means larger momentum. Am I missing something?
The speed of the object.
I'm not taking account of the speed of the object. And it doesn't say anything about speed of the object. So momentum does not just come from mass or velocity. It comes from both of them. Okay. So what does it mean is that you cannot decide based on just one factor. You have to look at both. If both information are there, then you cannot come up with a particular conclusion, okay? So that's why this is not correct statement. Could be correct if you know velocity, but since you don't know velocity, means you cannot say for sure that is correct. No. So this is conservation of momentum. That's great. Change in momentum of large mass is equal to change in momentum of smaller mass. Remember, this conservation of momentum came from this, actually. So this is also correct, okay? So remember, momentum, change in momentum is equal to impulse, okay? In collision, force is same and time interval is same. So that means change in momentum has to be same. So this is correct as well. So B and C correct means, in this case, it's the best choice is E, okay? So E is the best choice, folks. Okay. So this is one example of, let's say, conservation of momentum and a bit more. So let's watch this. I'm pretty sure you may have played with this toy, okay? I usually bring this in the class when we are in the class, but here I'm bringing this video. So notice, one out, and this coming from this height here, it hits one out, and it goes through about the same height. Did you notice that? Okay. Now, when two outs, when you are hitting with two of them, what happens? Two are getting out there and reaching about the same height. So what's happening? This one goes to higher height, means it has now gravitational potential energy. And when we let it go, it becomes kinetic energy, right? So it becomes kinetic energy. So this ball has kinetic energy, which is half mv square. And what happens? This ball has the same mass and it reaches same height, means it must start with the same speed. With whatever speed this one ball hit this thingy, okay? So speed, same means kinetic energy remains same. So kinetic energy before collision and kinetic energy after collision, they are same. And now that mass is same, and during the collision between all these balls, what happens? Speed remains same. So mass same, speed same means the momentum is also being conserved. Okay, so in this case, momentum is conserved and the kinetic energy before and after is also conserved. When we have this kind of collision, we call this elastic collision. So collision can be elastic and inelastic, okay? So if kinetic energy does not remain same before and after collision, then we call that inelastic, okay? So for example, let's say, so this is basically just picture of same thing we saw, right? So here, usually when we drop a ball from certain height, and actually, let's see if I can do that here on the camera on my table. Oh, not enough room. Okay, so here, let's say I drop it here on the table. Hopefully I do. And it's gonna bounce. Do you think it's gonna rise to the same height? If it does, then it's gonna come and hit my hand and I can just catch it without moving my hand down, right? So I already see some no over there, right? Okay, I see a lot of no. So let's try that. And meantime, think why no? Oops. Yes, of course, big no, but it kind of hit some wrong place. Let's try that one more time. Oh, I don't know if you even saw it, just bounced back up to this point. I dropped it from there, okay? So that means this is not an elastic collision. The velocity with which it hits the ground, it did not start with the same velocity. If it had, it would have raised to the same height, okay? It does not. Why? Because it loses some energy there, okay? Although the momentum may be conserved, the energy, kinetic energy, is not conserved, okay? So what happens is some energy gets transferred to the table there, okay? If I keep on hitting this table with this ball, then this table may be a little warmer. That means some energy is going there to, you know, in the form of heat. So if you had some sort of magic ball and it was coming up something like this at the same level, that means it would be elastic collision, okay? That would mean it is elastic collision. Usually these kind of collision are inelastic, okay? So now, if we have elastic collision, momentum is conserved and kinetic energy is also conserved, okay? Momentum and kinetic energy. So we already know how to write conservation of momentum, right? How do we write conservation of kinetic energy here? Not total energy, but kinetic energy. So we need to write total kinetic energy before collision and total kinetic energy after collision, right? So for example here, let's say this is mass 1 and this is mass 2, okay? So I can write M1 V1I, so that's the momentum before collision of mass M1, and I need momentum of mass 2 as well before collision, okay? So now this is total momentum before collision. And I can just copy this for the after collision by replacing I by F. So yes, so M1, B1, F plus M2, B2, F, right? So that's the equation. Now, how about kinetic energy? So rather than writing momentum, I need to write kinetic energy, which is half mv squared, right? That's all. So half m v1I squared, so that's the initial kinetic energy of mass m1. And I repeat that. And if you like, you can cancel all halves. There is half everywhere, so you can cancel that, right? So now, if you know it's elastic collision, then you can write these two equations. Now, by writing these two equations, theoretically, you can solve for up to two quantities, okay? Two quantities. You can solve for up to two unknown quantities. But remember, there is this b n square and like 4 terms. So solving these equations as such gonna be a bit challenging in terms of algebra, okay? But these can be solved if we know one of these is not moving at the beginning. So that means, let's say v1I is 0. If we set that up, then what's going to happen? Rather than being 4 terms in each equation, they're going to be just 2 terms and so on, okay? So we can use this concept and solve like this. So this is conservation of kinetic energy we wrote. We did not take account of potential energy here, but total energy is always conserved, okay? As long as we are taking account of all energies. And that's where this example of ballistic pendulum comes in. And let's watch this, and then we'll do a problem related to this. So ballistic pendulum, what happens? Let's watch this description.
A ball and a gun. So this gun is going to shoot the ball. The ball will get captured and held by the pendulum. And the momentum of the ball will then cause this pendulum to swing up to a certain height. And what you'll do in the lab is to measure that height and then use the conservation of energy and momentum appropriately to study the problem. So what we'll do is place this ball on the end of the gun and then try and cock the gun and then get this pendulum stationary and then pull the trigger and hope for the best. 0, 1, well, 3, 2, 1.
So what happened here? At the beginning, both have, like right before collision, what happened here? The bullet was moving, right? Let's say this gun, that is bullet. That ball is a bullet, or we can just say ball, right? So it was moving, but the catcher wasn't moving. It was at rest, right? And collision happened. And after collision, what happened? Both of these stuck together, started swinging. So collision, it started moving straight, but since it is tied there, what happened? It kind of went in arc from the straight. But the collision took place along the horizontal line. So that means for the collision, we can use conservation of momentum and find the speed right after the collision. Find the speed of this both objects right after collision. Now, once we know what's the speed with which it was moving, then we can tell how high it's going to go. So for the swing, so this is swing part, and this is collision part. So for the collision part, it's happening in horizontal direction, so there is no gravitational force affecting it, okay? So we can use conservation of momentum and write equation. For the swinging part, so total energy here is equal to total energy here, okay? So we can use conservation of energy, not just kinetic energy, but both kinetic and potential. Why? Height is changing. So when height changes, potential energy changes, so we cannot neglect. So when two things were moving horizontally and collided, in that case, height did not change, means potential energy did not change. So we did not have to worry about the potential energy in that case. We just wrote the kinetic energy. But here, both kinetic and potential energy changing. So for the swinging part, we can use conservation of energy. Kinetic and potential energy. So that's how we solve this problem. So the guy was talking about you use conservation of momentum and conservation of energy appropriately, not randomly, but appropriately where it makes sense, okay? So that's what he was talking about. So let's do it. So this is ballistic pendulum. So there is this mass not moving. It's like a M2 is like a catcher here, okay? M2 is catcher. And the ball moving with this speed after, you pull the trigger. So ball comes with that speed and hits the catcher. And catcher catches the ball and then it swings, right? So this is for the collision part. Okay, so this is for the collision part. What happens? So this is before collision. And this is after collision. After collision, what happens? Catcher is holding the ball. So that means both of them have same speed. They start with the same speed because they are together. Okay. So if we say this is the M1 and this is the M2, then in that case, this is going to be M1 plus M2, right? Whole mass. So it acts like one system, one object with total mass M1 plus M2. So if you like, you can just say uppercase M for that. Now it's like one object, okay? So for the conservation of energy, you don't need to separate. You can just write one, okay? And so let's first use conservation of energy. Is it done here? So for the collision, momentum is conserved, and that's what we're going to be doing first, okay? So what are the things we know? M1 is 2.50. Oh, block of wood. That's not M1, that's M2. My bad. M2 is 2.50 kilogram. M1 is bullet, see, based on how I have labeled it. But of course, you could, label differently. So M1 is 0.0100 kilogram. So that's the bullet, okay? So here what's happening is block is number 2 and bullet is number 1. So what are the speed? speed of bullet, and that's what we want to find, initial speed of the bullet. So that means V1I is what? Do we know V2I? Initial velocity of this wooden block. It wasn't moving, right, before bullet hit it. So that means it's 0. Yes, I see a lot of zeros on the screen. Okay, so that's a 0. So we know masses, we know the initial velocity of the block, but we don't know initial velocity of bullet. That's what we want to know, okay? And after collision, do we know what happens, the final thingy? All we know is after collision, it moves, it starts moving with a common speed because both of them are together. So I can simply write this here, okay, BF, and I don't know BF. It's don't know, you don't know this. And do you want this though? Are you asked to find this? No. So that's what I call don't know, don't care. But this becomes important. So you want to solve for that don't know, don't care so that you can use this in another equation so that you can get rid of it. Don't know, don't care. So don't know, don't care means in first step, you do care. That's what you want, okay? So let's use conservation of momentum. Using conservation of momentum, so let's write this. Total final momentum is equal to total initial momentum. What is total final momentum? This, right? Mass, final mass. If you like, you can write uppercase M, or if you don't want that, you can just write M1 plus M2. And the final speed, BF, which we don't know and we don't care, means we want this first so that we can get rid of this, okay? So that's the total final momentum. And what is total initial momentum? So they were separate. M1, B1I plus M2, B2I, and B2I is 0. Means this term is 0. So what do I know then? I know BF is M1, B1I, over M1 plus M2. Okay, so here what I have is VF, and there is VI, B1I, okay? So there is one equation and two unknowns. So that means we need another equation to fully solve it. And that's where this conservation of energy comes in, okay? So let's say if you knew, let's say all these, B1I, then you could just find BF. Or if you knew BF, then you could solve for B1I. If that is given, then that's good. You are just done, okay? Just plug in and get the number. But in this case, we don't know both B1I and BF. We don't know that. So two unknowns in one equation means we cannot solve that equation as it is. We need another equation. And that's where the second part comes in. Oh, those things were written there. How come I did not realize that? Okay. So now, the swinging part, that's where we use conservation of energy, right? So to use conservation of energy, what do we need? We need initial, we need final, and we need a reference. So that's why the initial height is 0, okay? So we are measuring height from wherever they were colliding and hasn't started going up. So that's what we are using as the initial height, okay? So initial height yi is 0. And final height yf is whatever height it rose, maximum height. So that's yf, okay? And the final velocity of both of these is 0 because we are talking about maximum height. At maximum height, it stops, okay? Now, how about initial? Initial velocity is equal to BF, final velocity. Does that make sense? I'm confused. Can somebody help me here? Don't say you wrote it, Ramesh, you deal with it. This is initial velocity for the swing part of this problem, right? So conservation, right? So the initial, total initial is equal to total final. So that's the energy, not the velocity, just velocity. It's the whole energy, right? But yes, if we are talking about whole energy, then yes, that would be the correct, okay, statement. So what's happening to this ball here? Oh, cats are here. Hey, cats are here. So what's happening? The ball comes here, right? And collides. During the collision, ball is inside the catcher, right? So now with whatever speed it starts moving, that's the end of the collision. That's the final portion of the collision, and we said that's the final speed. That final speed, BF, is the final speed for the collision. After collision, what happens? It swings, right? It swings and goes to a height. So swinging, for the swinging motion, with what speed does it start? Whatever speed it came out after the collision. So that's why they are same. So final is initial, may look confusing, but final from collision is same as initial for swing. So that's what it means, okay? So yes, it's a bit confusing, but I hope you understand that why the final from collision becomes initial for the swing, okay? So that's that. So after that, we are ready to use conservation of energy, okay? Total final energy, or whole F, is equal to EI. Here, this E means just mechanical energy, okay? So for the swinging part, what's happening? After it starts swinging, it's not colliding with it or anything like that. Just the kinetic energy gets converted into potential energy. And what potential energy? Just gravitational potential energy, okay? So final kinetic energy, final means half total mass times velocity squared. Did I write that? No. So half m1 plus m2. See, both masses are together. And, oh, maybe I could have just first talked about this here. So final is this, and final speed for the swing is 0. Means kf is actually 0. And initial height is 0. So it starts swinging from 0 height, means initial potential energy is 0. Remember, this is mgyi, and yi 0 means this whole thing is 0. So that means we have just this. So that way we don't have to keep writing a lot of things here. So what's the final potential energy? Potential energy mgyf, right? Final potential energy UF is mgyf. But M here is two masses, mass of bullet and mass of block. So that means I need to write M1 plus M2 as the mass and GYF. How about initial kinetic energy? So this is the initial kinetic energy of this thingy there when it starts swinging, right? And it was moving with this speed here. Half m bis square. Oh, m is what? M is two masses, m1 plus m2. So now bf, or let's say bis square. So I, for the swing, that's the initial kinetic energy, but that is final speed for the, they are saying final speed for the collision. And that's what we are looking for, VF, okay? Oh, one thing I can see is M1 plus M2 inside parentheses, M1 plus M2 inside parentheses. If it was like, if we had written this as uppercase M, this would be just total mass, right? So what it means, it's multiplying everything, means we can cancel that. Just the mass portion, leaving just this one here. Half BIS, which is same as VF, means I can write BF square. Why BF square? Because our previous equation has BF in it, and we want that, okay? So VF is 2GYF under the square root. So I'm just solving for VF, bringing G2 here, 2 times that, and take the square root, okay? So that's VF. So let's see, if I remember VF from collision part, VF was M1 plus M2, or not M2, just M1, I think. V1 did I write V1I or VI1? I forgot. Okay.
I had it as V1I.
Okay, V1I, great. Okay, so that's that. And down here, I think we had M1 plus M2. Okay, so I'm just copying the equation that's in the previous slide we wrote. Okay, so now this VF is same as this VF, right? So what that means? That means 2GYF under the square root is M1 V1I M1 plus M2. So now we know everything. See, we know YF, we know masses, G of course, we know that. So what it means? That means now we can find the speed of the bullet. little bit rearrangement here. So this mass is gonna go up there and multiply. This mass is gonna go down there and divide this whole thing. 2gy f under the square root. Yes, so that's gonna be the answer. Okay, so we know masses, so you can use that and calculate the speed. Hey, let's say if you are gun loving person, I don't own gun, okay? But just in case, let's say you are a gun loving person and you bought a gun and you wanna find out how fast bullet comes out of this gun, right? So that's the initial speed, let's say. So if you wanna, let's say, find that, what you can do is you can set up this ballistic pendulum kind of situation, wooden block, and shoot on the wooden block, right? Be careful, don't do the, make sure not, no accident happens, right? And then see how high it goes, right? See if you can measure that. Once you know that height, you can just plug that in there. And if you know the mass of the bullet and block, which you can weigh, right? You can tell how fast bullet is coming out from the gun. I don't know if the manual tells you how fast the bullet comes out, okay? I don't know, okay? But anyway, so that's that, folks. So that's how we use conservation of momentum, okay? Looks like this is break time, so let's take a break, okay? And we're gonna move on. So I'm pausing the recording. Later, remind me to start. Okay, 30 more seconds, folks. Oops, I'm blocking, I'm guessing. Five more seconds. 5, 4, 3, 2, 1, and it stops. Let's see what we got here. Oh, nice. Bright is here. I like this kind of question. So one has double mass of the other, and the motion is starting by pushing each other. Initially, both of them are standing, means total initial momentum is 0, right? Velocity of 1 is 0, velocity of 2 is also 0. So total initial momentum is 0. So total final momentum has to be also equal to 0, because total final is same as total initial, right? So since total initial is 0, total final has to be 0 as well. So that means if one has positive momentum, another has to have negative, so that total becomes 0. It's not just positive and negative, and it has to be equal as well to add it to 0. So since mass of one person is double of another one, the speed has to be half. Massive person gonna have half the speed. So that's why it's 2 meters per second. Half of 4 is 2. And direction has to be opposite, isn't it? When you push somebody, you get pushed back, right? So looks like that's why So let's see, gives Jack himself a speed of 4 meters per second, and Jack is pushing Matt so Matt gets pushed right. And are we looking for the direction of Jack or Matt? So Jack velocity means it has to be opposite of Matt. So it's left. So 2 meters per second left is the correct answer, right? Which is B. But we got 8 to the right as well and 8 to the left as well. So somehow we got double, right? So let's see if I can write it here without making slideshow. Okay. So total final is equal to total initial, and total initial is 0. Why? Both.
Because they both start at rest?
Right. Both are at rest. So this is going to be, let's say, Matt is 1 and Jack is 2. So that means mass of Matt times the speed of Matt, which is final, plus mass 2 and speed 2 final must be equal to 0, right? And here we are looking for what is Matt's speed after the push. So we are looking for Matt's speed and Jack's velocity, bit confusing. So Matt's speed means we are looking for B1F. So this is going to be B1F is negative M2 V2F over M1, right? And M2 is, let's see, with Jack is 2, has mass M, so that means it is negative M over 2M, M1 is 2M, Matt, and Matt is 1, right? And B2F is 4 meters per second. 2 makes this 2 and mass cancels. So what it is saying is the velocity of 1 is opposite of velocity of 2. That's what this negative sign means. So if one has right, or if one is going right, another one is going left. Okay, so that's what it means. Okay, so there are a couple example problem here. So for example, here you can do the bullet test, speed of the bullet test, looking at this. But in this case, there is friction. So here, I'm not doing this problem, but to do this problem, what you need to do is you need to use this energy concept, remember? And since the height is not changing, it's going to be 0. So this for the energy, and also need to use conservation of momentum. So use these two concepts and solve this problem. So it's going to be a little bit long, okay? And do I know the answer? Answer is around 400 meters per second, okay? Around that. So it's for you guys to, let's say, do some practice. if I ask this kind of question, I'm not going to be asking this whole thing. I may ask just this part, which is conservation of energy, which we already covered, or just this part, okay? But you can combine both of these to solve this kind of problem, just as an example, okay? So I like to kind of move on, okay? And there is this very simple, although it's a long, but kind of simple problem about conservation of momentum. And totally elastic collision means what happens? They get stuck, just like in case of that ballistic pendulum. That's totally elastic collision, okay? So you use that concept and do that. And two-dimensional collision is basically one-dimensional collision, just in components. So that's that. So I'm not gonna ask that you in the exam, okay? Just keep that in mind. Rather, what I like to do is I wanna move to the torque for this half portion of this class, okay? I think with this information, I think there is enough information to use conservation of momentum and conservation of energy, okay? So inelastic collision. So inelastic collision, I talked about it, right? So if kinetic energy does not remain same, it's inelastic collision. And inelastic collision can be totally inelastic collision when both of them get stuck. Keep that information, okay? And using conservation of energy conservation of momentum is same idea. So look at that example, okay? It's done there, so I don't think I need to read that. So that's why I'm leaving that for you guys, okay? So in the exam, maybe or maybe not, it's gonna be, if there is, it's gonna be in the very simple form, okay? Just basic idea. So, am I sharing the screen fine, I'm guessing? Looks like yes, I am. I'm recording. So now let's move to the torque, okay? So let's start that by watching this very brief video of opening the door. So yes, there is no sound in this video, okay? So there is hinge, right? And there is knob. So the guy bumps in this door here, applies force. The door wouldn't open. And then when the force was applied over there, it was really, really easy to open it, right? So where you apply force matters. So when you try pushing your door, usually you push near the end over there. Even when it's, let's say, unlocked totally, push a little bit, okay? It's not, attached over there. When you push it, you usually push it here. And when you push it here, it's easier to open the door. If you try pushing it here, not so easy. If you try pushing it here, not so easy. You need to apply larger amount of force. Now, let's see what this guy does here. So has to apply a lot of force while pushing right near the hinge. So that's what it is showing. So where you apply force matters. It's not just the force matters, but where you apply force matters in case of rotational motion. So we need to take account of that. So when we take account of not just the force, oh, is this another one? Yeah. So now you apply a lot of force there, see? What direction you apply force also matters. You apply the force, door is not rotating, see? It's not rotating. And by the way, this is from the YouTube channel called Flipping Physics. It's awesome. This guy has done very awesome job, and it looks like he knows physics. Yes, I know some channel, they do the physics and they may not be talking it correctly. Most of them do. But I have watched a couple of videos while I was searching for the video for the demo. He has done very good job. And he explains it very well as well. I like that, okay? And my previous slide, this one has that link. I don't think I have posted this. I added this once we went online. When I was in the class, when we used to be in class, I used to push right there, door on the classroom, okay? But now I cannot do it on the camera. So I have this video. I had to look for this video, so I found this video here, okay? And this channel here, Flipping Physics. So that's the name of this channel. Okay. So it's basically same thing, but here is stationary, right? So we already talked about it, so I don't need to do that. So what it means is, it's not just the force matters, but where you apply force and what direction you apply force matters. So when we bundle all those three, how much force we are applying, what direction we are applying the force, that's the angle, and how far we are applying the force from axis of rotation. All those three things matter. So when we combine all those three, what happens? We get this. And that quantity is called torque. Okay, so force, just force. Now torque takes account of force and direction of force, you know, with respect to, let's say, when we are trying to rotate, which way we are trying to, you know, which way we are applying the force, that direction matters. So it takes account of that one as well. And how far, that's R. So in this picture, you see here, this is called torque wrench. I don't know if you guys know it. If it has very, so there is wrench and there is torque wrench. So if there is long handle, R is larger. So that's what it makes torque wrench, because R larger means torque is larger. Okay, so that's why the name torque wrench. Okay, so where the force is acting, that's the R. What direction force is acting, that's the angle. Okay. And of course, how much force you are applying. All those three matters. So when we bundle them together, that's what makes the torque. Okay. And this point is called axis of rotation. So in case of door, the hinges, the line passing through the hinges, that's the axis of rotation, right? Do I have something here I can spin? I don't know. I have this here. Oh. It doesn't like that color. Okay, this one here. So when it is spinning like this, it's spinning about the center. So axis of rotation would be center, and you know, this pen passing through the center when it's spinning like this. So axis of rotation for this here, what's happening? What is rotating? Yes, of course, we are trying to just rotate the bolt here. But of course, at the same time, this thing has to rotate that bolt, okay? So this is axis of rotation here. And this R is distance of the force from the axis of rotation. That's the R, okay? And the angle, see this both R and F, they are vector. So although I said this was a distance, see it is basically what we call position vector. So how far it is from the axis of rotation, it is a vector. So what is direction of this vector? This vector is going away from the axis of rotation. So now this angle gonna be this angle here between R and F, not this angle, rather this angle. So why not this angle, rather this angle? Because it's the angle between R and F. What is direction of R? That's the direction of R. And this is the direction of F. So we need to look at this angle here, okay? So now, do you guys remember we had work done as force times displacement times cosine of angle between them? Do you guys still remember? Hey, this looks a lot like that, but there is a difference though. This product of force and displacement is giving us work, which is scalar. Over here, the product of that position vector and force, and position vector looks more like a displacement here when we look at the notation. What happens? Both of these are vectors. We are multiplying R and F, and we are getting torque. And torque is also vector. See, this may be rotating this way, or this may be rotating that way. So the torque has a direction clockwise or counterclockwise. So we can choose one as a positive, another one as a negative. So it looks like work done, but it is not. But it's a product of two vectors giving us new vector. When we have this kind of vector, product, we call that vector product. But when we multiply two vectors, and if we get scalar, then we call that scalar product. So when we have a scalar product, we pick up cosine. And when we have vector product, we pick up sine. But we have to keep track of the angle correctly, okay? Sometimes torque may have the angle cosine theta. If we are not looking for this angle, rather we are looking for this angle, let's say, then torque could be written in terms of cosine theta. Okay, so that may happen. So keep that in mind. So this sine theta is not totally absolute. It's sine theta when we look at this angle this way between R and F. Keep that in mind. And if we are to combine F and sine theta, then it's going to look like a component of force. When we combine R and sine theta, it's going to look like a component of this R vector, right? One of the component, opposite side component. So in fact, we write the torque in those three different forms, okay? We can write torque in three different ways. This one is 1. And what are other two? We combine sine theta with either R or F. Let's look at first by combining with F, okay? So let's combine with the F. So when we look at this is a component of force. Which one is that then? So this being the angle, then what's gonna happen? For this is gonna be, let's say if I were to make with this one here, I go like this, I go like this, right? So with this angle, this is going to be adjacent. And this is going to be opposite. So this one picks up sine. So this here, which is same as this one here. So while writing component, what are we doing here? We are choosing one component along the R. We call that radial component, just like in case of circular motion. Another one is perpendicular component or tangential component. Okay, so this becomes f sine theta. This f sine theta is this component here. Which one is that? The one that makes 90 degree with the R. We call that perpendicular component. Okay. F perpendicular. So that's what it means. If the force is already perpendicular, for example, let's say this is R and F is already perpendicular, that's good. So that means torque gonna be just R times F, because the angle between them is already 90 degree and sine 90 is 1. So torque becomes just R times F. So when does that happen? When F is perpendicular to R, normal to R, okay? So that's another way to write it. Now there is one more way to write it, and we're gonna be using that a lot. This one here. So now you pair sine theta with R. That means we are looking for the component of R. So how do we do that? So for that, you need to recall 2 or 3 steps here, okay? So we want to draw this R sine theta. So how do we do it? First, you label this. Did I write those things here? Yes. You first label this axis of rotation, okay? And next, you draw line of action of force. So this is step 1, if you like that way. This is step 2. So what is line of action of force? Hey, it's nothing, you're just making that force longer, okay? Force is just acting in one direction, but you can draw that line in both directions, both sides, okay? So it's just the extension of force. So that's what that is. So that's the line of action of force. That's the step number 2. Now step number 3, that's important. And usually that's when students make mistake. So you want to be one of that student who makes mistake while drawing this? Probably not, right? So let's pay attention, okay? Even if you are kind of, let's say, in middle of something, thinking something like that, for now, finish that thinking and give me 100% just for a minute, okay? So third step is to draw line starting from axis of rotation, which you have already marked, to the line of action of force, which already you drew in number 2 step, right? But you can draw several such lines. So which line you want, that's the one thing that's important. The one that makes 90 degree to the line of action of force, okay? And that's gonna be the shortest line. By doing this, we are making 90 degree, means now this is our right triangle, and this is gonna be that component, sine theta component. See that? So that's how we are drawing. So it's not obvious yet. So this angle theta means this angle theta. Now for this is opposite, right? So that's why this is R sine theta. That is R sine theta. And it has a special name. We call that lever arm. We call that lever arm, okay? We call that lever arm. So how do we draw lever arm? One more time. Start from axis of rotation and go to the line of action of force. From axis of rotation to the line of action of force, such a way that it makes 90 degree to the line of action of force. And that way it becomes shortest, okay? So that's why it is the shortest line drawn. Shortest line when angle is 90 degree, when this angle is 90 degree, okay? So that's the lever arm, folks. So lever arm can be sine theta, r sine theta, or cosine theta. For example, rather than knowing this, if we knew this one here, if you are given that angle, then this would be adjacent for that, remember. So it depends on what angle you know. So it's not always sine theta. Keep that in mind, okay? Hey, we know how to find torque now. Let's start by finding the lever arm first. Lever arm for this force in this drawing, okay? So axis is already marked for you. All you need to do is draw a line of action of force, draw lever arm, and figure out what that is, okay? So here is 2 minutes for you guys. Are you guys drawing that with those steps? Please draw it, okay, rather than just randomly choosing the answer. And we are looking for lever arm here. 30 more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got. We got all of those. Okay, let's do it. Looks like we need a little practice here, right? So first step, that's step 1, which is just labeling or marking the axis. That's done for you. Step number 2, draw a line of action of force. Third step, draw a lever arm. Starting from axis of rotation to the line of action of force so that it makes 90 degrees. So in this case, that's going to be the lever arm. And that's the shortest one. So now it makes right triangle. And we want this length here. Lever arm is the length, shortest length from the axis of rotation to the line of action of force. That's what the lever arm is. Now for this angle, this is adjacent. Okay, so adjacent means it's going to pick up cosine. And we are not looking for torque. If we are looking for torque, then you multiply lever arm by force. Here we are just looking for lever arm, no torque, right? So the one that has force shouldn't be there. Lever arm is just a length. So there shouldn't be force, okay? So now one with the cosine gonna be the correct answer, which is D, just like most of you identified it, but there was confusion. Okay. So now this one
I
here,
have a question.
yeah.
So is the torque range the same as the lever arm, or is that a different thing?
Torque wrench, so length of the torque wrench is not lever arm. It has to be shortest distance to the line of action of force. So the length of the torque wrench is this, R, that's what that is.
Oh, okay. Yeah, I understand. Thank you.
Right. So now here is very similar. This time we are looking for torque, okay? And to find torque, you need lever arm, okay? So go ahead, draw and answer this. This time 1 minute and 30 seconds. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay. Let's see what we got. So this time mostly C, but there was B as well. So what's the difference between B and C? One is lever arm, another one is torque. Okay. So one is lever arm, another one is torque. So B is lever arm, but we are looking for torque. Okay. So if we are looking for torque, we need force there. So without force, the one that doesn't have force, nope, we're not looking for that. So either it's going to be this or this. Now is it sine or cosine? So for that, axis is already level for you. Draw a line of action of force and draw the shortest distance, making this 90 degree. Okay, so that's lever arm. Oh, not lever, but lever. Okay. And this is opposite side. It picks up sine. That means, yes, C is the correct answer then. Okay. So R sine theta is labor arm. Labor arm times force is the torque. Okay, so that's why C is the correct answer this time. Now, so you have a minute to answer this question. We are kind of, yeah, a minute. Thirty more seconds. And 5 more seconds. 5, 4, 3, 2, 1, and it stops. Okay, let's see what we got here. Interesting. B, C, and D as well. No A though. Okay, just 2%. So let's see. Correct answer is B in this case. So let's see. Let's talk briefly why. So torque is labor arm times force. So the bicyclist, you know, is the same person. So we can say, okay, force is constant. So we can assume it's applying same force, right? So now, wherever labor arm is longest, that's going to be the most torque, okay? And remember, when you are pedaling bike, if you haven't paid attention, next time, pay attention, you are pushing the pedal down all the time, not sideways, all the time. No matter where the pedal is, you are pushing it down. So force is down here. Force is down here. Force is down here. Force is down there, okay? So now, if I were to draw a line of action of force for this force, oops. So I think more accurate would be there, right? So line of action of force passes through the axis of rotation. So it's like pushing door directly towards the hinge. It's like a situation when you push door directly towards the hinge. Door won't rotate that way, okay? So yes, you are applying the same force, but torque is 0 because labor arm is the distance from axis of rotation to the line of action of force. They are at same point, means labor arm. It's the same thing for this one as well. So labor arm for A and D, zero. Now for the C, that's the line of action of force. This is the labor arm. And for B, this is the labor arm. See, this is the labor arm. So that's the longest one. So that's why B is the correct answer. Okay. Okay, so let's leave it here. We're going to pick it up from here next class. And I think next class is going to be the last class before a midterm. I need to double check, but I think that's going to be the case because the other one going to be review. I hope I got it right, but it's on the syllabus. I'll double check.
Yeah, that's correct, Dr. Jungana, you're correct.
Okay, thank you, Carl. Otherwise, it's on syllabus. I can check syllabus and you can check syllabus too.